Welcome back to biology. This is Mr. Kubuske again. We've been talking about evolution. The last time we got together, we talked about Darwin and his theories of natural selection. And at the very end of the presentation, we talked about his book on the origin of species. And we talked about how he waited late into his life until he published that book. Well, there were two reasons really that you could theorize why he did that. One, obviously, because he was a very religious person, worried about persecution from the church. But the other one was, and you'll find this out a little bit more if you read some articles about him, is that he really wanted to make sure that he had really strong evidence to convince people. He didn't just want to say this willy-nilly and have people, throw it back in his face without being able to back it up. And have evidence for what he had to say. So today we're going to talk a little bit about some of that evidence that for the theory of natural selection and the idea of evolution and where those came about. So here we go. So obviously the first and foremost, and the first one Darwin pointed to himself was fossils, the fossil record. Okay, and now fossils, in case you're not aware, and I'm sure you probably are, fossils are remnants of once living organisms. Here's an example of a fossil here. Okay. Now, fossils can be casts or they can be molds. And what that means is, like you can see in this picture, this is of the Archaeopteryx, the link between dinosaurs and birds, actually. Technically, he is a dinosaur, but he has bird features. And well, anyway, that's for another time. But you can see, you can still see the impressions of his feathers here around him, okay? So those leave that mold for us to fill. And the bones, obviously, they leave those gaps. Well, the bones, as I look at this, those aren't actually bones. They're just the shape of bones, but they're rocks. Because what happens is over time, the bone decays and is replaced by this rock material. Okay, so when you actually are looking at a dinosaur bone in a museum, you're actually looking at a rock in the shape of the dinosaur bone. Okay, that filled in that gap. So in other words, you're never actually seeing the bone itself. You're seeing a cast or a mold. Okay, so fossils can be just about anything that's any remnant of a once living organism, but most commonly we refer to fossils as things like bones, tree bark could be an example, shells, whether it's like the shell of the organism itself or like eggshells, like in this example of the dinosaur eggshells, and even like traces of the organism, like poop. This is dinosaur poop. Okay. Now, the important part about fossils to evolution is that it shows the relatedness, okay, of organisms, current organisms, to their ancestors, and it shows us the steps in between. Now, it's important to note that the fossil record itself will never be complete. We'll never have a fossil for every organism that's ever lived on the planet, so there will always be gaps in the fossil record. And the reason for that is it's really, really hard to make a fossil. It takes millions of years. The organism has to die in the exact right place at the exact right time under the exact right conditions for it to happen. And this little animation kind of gives you a feel for how fossils are formed and how they're found. Okay, so you have your dinosaur here, dies in a sandy, swampy area. That sandy, swampy area becomes flooded, and different sediments pile on top of that dinosaur. And over time, more and more sediment piles on top of him. He gets compressed into that rock layer, and over time, again, his bones are replaced by rock. And then hopefully, there's a shift in geologic conditions, and the rock layer becomes visible to us and we can find the fossil. But that's basically how it has to happen. So fossils can only form and be found in sedimentary rock, basically because the rock is forming. You build sediments on top of each other to build a sedimentary rock, and anything you put in between as you're building is going to be trapped there forever. And fossils, again, are actually rock that replaces organic material. Now, there's different ways to tell the ages of rocks and fossils and things like that, and we do that by dating. And no, I don't mean what you and your boyfriend or girlfriend do, okay? I mean dating, like figuring out the age of these different things, okay? So relative dating or relative age doesn't mean that you date your cousin. What it means is that you can figure out the age of fossils based on the rock layer that you find them in. Obviously, rock layers lower are older than the rock layers above. Now, that's not always the case. We'll talk about that here in a second. But in this picture, obviously, you can see these nice straight lines of rock layers, different sediments that have piled up over time. The oldest ones obviously have to be at the bottom. So if I find fossils down here at the bottom, those obviously have to be older than a fossil that I would find up here at the top, okay? Because they obviously over time they build up. Okay, so here's an example of a rock layer. See if you can figure out which ones are the oldest and which one's the youngest. Kind of work your way through it. Now, if you go through it, you would realize that I is the oldest, B is next. Okay, even though there's a shift and B ends up down here, what probably happened is there was an earthquake or some geologic condition that happened that caused the rock layers to change. Position. So it goes I, B, F, Then M, H is a lava flow, okay, an outflow of lava and left some magma on the surface, and that hardened became rock. And then R is the surface rock, so it would go I, B, F, M, H, R if you were looking at it, okay? Actual dating or actual age comes from carbon dating or radioactive dating. And what that means is you can measure the different amounts of radioactive material left in an organism. And it's based on half-life. So what do I mean by that? Okay? Now you inside your body, and I apologize if my picture's getting weird, okay? Inside your body have radioactive material inside you. It's called carbon-14. It's different than carbon-12, which is the one you see on the periodic table. And if you watch my chemistry videos, you'll learn a little bit more about why those things happen. Okay? But basically what happens is carbon-14 is radioactive, which means that over time it will decay, it will lose pieces of itself. That's why we consider it radioactive. Now the amount of time it takes for half of that material to decay or disappear is called the half-life. So the half-life for carbon-14 is just over 5,000 years. So if I found a dinosaur fossil, or if I found a rock and things like that, and I want to know the age of it, what I could do is I can measure the amount of carbon-14 compared to some of the other isotopes that come from carbon-14 to figure out its age. For example, if I found a body, and I knew that it started off with 16 milligrams of carbon-14 in it when it was died, okay? When it had died, excuse me, okay? After 5,000 years, half of that carbon-14 would be gone. So how much would I be left with? Well, I'd be left with 8 milligrams. Okay? Well, what happens after another 5,000 years? Is it down to 0? No. Remember, this is called a half-life. So you take the amount that you have and you divide it in half. So now, after another 5,000 years, after 10,000 years total, I'm down to 4 milligrams. After 15,000, I would be down to 2 milligrams, and after 20,000 years, I would be down to 1 milligram of carbon-14. Now, technically, if you do the math, it would never become 0, but it would be probably eventually get really, really close to a 0 number and to having no carbon-14 in it. So you can use carbon-14 to measure the ages of things that are relatively young, geologically speaking. If you want to measure anything older, like in millions or billions of years, then you got to go to some bigger isotopes like uranium-238. Uranium-238's half-life is 4.5 billion years. So when we collect space dust and debris from outer space, or collect rock samples from deep rock layers and try to figure out their ages, we use uranium-238 to figure out their ages. And that's how we can tell things like the age of the Earth, the age of the solar system, and the age of the universe. Okay? Now, last thing you should know about fossils is you can actually use fossils to figure out the distribution of organisms over time. That's called biogeography. And what happens is that you can study where the fossils end up in certain rock layers and see if they appear in the same rock layer but on different continents. And what that tells us is that the continents obviously were all once connected into supercontinents. That happened actually a couple different times. The most recent one we know is Pangea. Okay, so it's no coincidence though, but if I look at these fossils of these different ancient organisms, that I can find them spread in this pattern, so that kind of gives us the idea of how Pangea came together and eventually split apart. And we can still do that today, biogeography, looking at the different organisms and how they're spread across the continents. Now, there's another way to show relatedness or evidence of evolution, and that's through morphology. Now, take a look at this picture. Okay, well, what do you see? Well, I see two cats. Okay, well, obviously they're cats. They have whiskers, they have fur, they have pointy ears, they have a nose similar, they have eyes that are similar, they have paws. You can say that they have lots and lots of similar structures and similar appearances. But at the same time, they have a lot of little differences too that make them unique. So these are actually two different species of cat. We have a domestic house cat on the right, and we have a lion cub on the left. Okay, those are obviously two different species. But they have similar structures, so that tells us that they're probably pretty closely related. Those structures that they have in common that come from a same ancestor, those are called homologous structures. Okay? This would include anything that, again, you get from an ancestor that your cousin or another species similar to you also has. Okay? You can be something as simple as the two eyes that we have and two ears to something as complex as, our opposable thumbs and things like that. Okay? If you have it and someone else has it, that must mean you're pretty closely related. An example here is the bones of our arm. Okay, the bones in our arm match the bones of the arms of different organisms that we're pretty closely related to. But I could go even further with this, and I could look at like an alligator's arm, and they have similar bones in them, so that would tell us that we're related to them. Okay, now are we as closely related to alligators as we are to bats, whales, cats, and other things that are mammals? No, because we have more homologous structures in common with mammals, which means that we're more closely related to them. So the more homologous structures you have, the more closely related you are. Analogous structures are structures that have a similar function but come from a different origin. An example, obviously, here is a wing. Okay, birds, bats, pterodactyls, and insects all have wings. Does that mean that they are all related? Well, they are related, but not because of the wings. The wings come from different places. Like a bat's wing is actually formed from the webbing between its fingers. A bird's wing comes from the extension of its arm. Okay, a pterodactyl, actually, its pinky was elongated, and a webbing came off of that, and that's what gave him his wings. Okay, and obviously, an insect's wings are a different, complete appendage from the rest of his body. So analogous structures don't necessarily show relatedness, but what they do show is adaptations. Like this obviously is an adaptation that they have gained because they fill a certain niche in their environment. And so this is an adaptation that they need to have for survival, and that's why they have developed these wings. So analogous structures, similar function, different origins. Okay. Vestigial structures are really the pretty cool ones to talk about. These are structures that your ancestors needed, but you don't. These are things like your appendix. Our ancestors needed them probably for something like digesting raw meat, where we're almost positive of certain roles that the appendix had. We're not quite sure exactly. But since we don't need it anymore, it's actually getting smaller and smaller. And there are people being born now, that don't have an appendix. Your tail, you don't use your tail. You have what's called a vestigial tail or a tailbone. It's curved up inside you and you just sit on top of it. It just has gotten smaller over time because we haven't needed it. So if you don't use it, you lose it. Wisdom teeth, body hair, your erector pili, your goosebumps, okay? Those are an evolutionary trait that has been passed on to us that we don't necessarily need anymore. And even your pinky toe, yes, your pinky toe. There's theories out there that in a few thousand years, hundreds of thousands of years, your pinky toe will be gone. Other examples are a whale's pelvis. Yes, whales have a pelvis. It obviously doesn't stick out. They don't have those lower appendages that they use, but they still have the bones in there, which tells us that they must have had these pelvis at one time. They must have had lower limbs at one time, which tells us that they must be related to other organisms that have those lower limbs. Okay. Last two things, embryology. Okay, just look at the top picture. Okay, obviously I have the names of the organisms up here that are all different, but if you look at their embryos, what do you notice? They're pretty similar. They've got gill slits, they've got eye sockets, they've got tails, they've got a bulging belly. Okay, they have a lot of similar features. Now, as each one develops, they start to become more unique. Okay, and obviously they become their own unique species by the end. But it's no coincidence that their embryos looked the same at the beginning because they must be related somehow. Now, the more closely related you are, the more closely your embryos should look to your relative. Okay, so development of related organisms will be similar. That's embryology. And then the last piece of evidence that we have for natural selection and evolution is your DNA, your amino acid sequences and things like that from protein synthesis. Okay, the more DNA you have in common, the more related you are. It's that simple. You share about 97% of your DNA with a chimpanzee. That's no coincidence then that they're our closest relative. You share in the 90s with monkeys. So when people say, oh, humans evolved from monkeys, that's absolutely not true. We have a common ancestor with them. We know that because we have homologous structures with them and we share a lot of our DNA with them, but we in no way evolved from monkeys. We have a common ancestor. Monkeys are their own species. Actually, our closest relative is the chimp. But you can see down here some other animals that we are related to and how closely related we are. So the more DNA you share and the more amino acid sequences match, the more related you are. It's that simple. Okay? So that kind of wraps it up. Evidence of evolution. We talked about some different things: fossils, biogeography, morphology, homologous structures, analogous structures, vestigial structures, embryology, and amino acid sequences. All of these things helped back up Darwin. So when he finally did publish his book, he could say, "All right, here's my proof, guys. Okay, I know that this is the way that things happen, even though you can't actually see it with the naked eye." Hopefully, you learned something. In the next section, we'll talk about the different types of evolution that take place, or the types of natural selection that take place, and I look forward to talking with you then. Have a great day.